Okay, picking up where we left off in our 1.4 notes, talking about left hand and right hand limits and continuity. Okay, so these are pretty classic like AP problems. I've seen them pop up on like a lot of previous like multiple choice questions from old exams, and they're pretty good problems. So what they want us to do is they want us to find the value of a, this variable a here, that will make this function, this piecewise function, continuous. Okay, so I just started you off with a little hint. Basically what we want to do is we want to force the left and the right hand limits to match as x approaches 3, because that's looking like that's where the break in my graph could be, okay, where my little jump discontinuity could be, or hole or something like that. So what we're going to do is we're going to take our limit as x approaches 3 from the left side, which in that case I'd use this piece, because those are my numbers that are less than 3, so that'd be where 3 is coming in from the left. And I want that to be the same as my right hand limit, which is when x approaches 3 from the right, which would be the second piece, because those are all the x values that are greater than 3. So I'd use that 2ax piece of my function, and I need these to be the same. Okay, that would make my function continuous. And that's anytime we're asked to find a limit with piecewise functions, we kind of have to split it up into the left and the right hand because we have like this break in our graph. Okay, so we can direct substitute from here. Here I'm plugging 3 in for x. All right, 3 squared minus 1, I get 8. Over here, I get 6a. So solving for a, divide both sides by 6, I get 4/3. Okay. So if x was 4/3, or I'm sorry, not x, a was 4/3, our function would be this. Our piecewise function would be the top doesn't change at all, but I have 2 times 4/3, which would be 8/3 x. So basically what we just did there is now, if we were to take the limit of both sides, they would both equal 8. So we basically made the graph meet when x equals 3. And then just to kind of like double check, you could always like figure out, okay, when I plug in 3, do I still get out 8? Because that's kind of one of our pieces of continuity, like whatever our limit is has to be what the output is as well. So if I want to find f of 3, I would use this piece because that's when x is equal to 3. And we get 8. And that's what our limit was approaching. And obviously if you plug it back in here, you'd get 8. So then the left hand, right hand are the same, and so is the output. So you just made that continuous. Okay. So I always kind of just like to double check the value of whatever we're trying to kind of like make the graph meet, whatever x value we're trying to make the graph meet, just to make sure that I got the right number there to do my math correct. Okay, let's do maybe one more of those. So this time, it looks like my possible discontinuity would be at 0. Okay, so let's start with looking at the limit as x approaches 0 from the left. Which piece would I use for that, top or bottom? Top, yep. I want that to be the same as my right-hand limit. Limit as x approaches 0 from the right, which I'd use this bottom one. Okay. I'll let you guys take it from there. Oh, careful with this one. This is one of our special limits. That's 1. So it ends up being 4 on that side. I like that one. Okay. Over here, and I plug in 0. A would have to be 4 in this case. Okay. So if I were to rewrite that piecewise function, with plugging in that value, I get for A, which was 4, minus 2x. Okay, folks, just as a check, go ahead and find f of 0. See what you get. Dalton?
It would just be 4.
It would just be 4, which that's what we wanted, because that's what that limit was approaching. And again, obviously, if we were to plug 4 back in here, that makes the left and the right-hand side the same thing, which makes the limit exist. And then my value is defined there as well. Okay. The last thing, I like those problems. The last thing we need to talk about with this lesson is one of our big 3 theorems, as I like to call them. There's like 3 really important theorems that we talk about throughout the year, and this is like the very first one, so it's a pretty exciting thing for you guys. Okay. I'm not a big fan of doing a lot of like really intense like algebraic proofs because it's like good for you to kind of like see where it comes from. At the same time, a lot of it feels not necessary to like go through all that. I kind of just like to like look at pictures and more like conceptually understand like why this theorem exists. That's what I'm going to kind of lead you through for the next couple slides here. Okay, so we know that this function over here would not be continuous, right? I have this gap right here. What type of discontinuity would we classify this as? Jump. Yep, exactly. Jump discontinuity. So the function doesn't take on, so I'm going to phrase this, it doesn't take on all of the values from our endpoint here when f of 1 is 0 to our other endpoint here when f of 4 is 3. Okay, we can see it's kind of missing this gap right here of outputs in between 2 and 3. Okay, so obviously it's not continuous. Instead, let's consider a function that is continuous from this interval of 1 to 4 and just give a possible sketch. Okay, you can do the same sketch as me if you want. You don't have to. I'm going to make it pretty basic. I'm going to say we're going to start here at 1, end up here maybe at 4. I'm just going to kind of make it like a little curvy, something like that. I don't know. Keep it simple. Okay. So for your sketch, consider where f of 1 and f of 4 would be. That one. There we go. So f of 1 would be my output here. So let's label that on our y-axis. That'd be f of 1. And f of 4 would be your output wherever you put that point for your other endpoint there. F of 4. So as long as your sketch is continuous, meaning you can trace it from 1 to 4 without picking up your pencil, that's all you need for this little mini proof, I guess we can call it. So here, since it's continuous, what can you say about the values between f of 1 and f of 4? So between these two values, we can see that we have an output for literally every single number in between those two outputs, right? If it's continuous, I'm going to have an output that's like just above f of 1. Halfway, just below f of 4. If it's continuous, if I can trace this with my pencil, my function's going to take on, I think that's what this is, take on every value in between f of 1 and f of 4. If it's continuous, right? That makes sense. Even if it did something weird like this, you don't have to write this down, but even if it went like, okay, it's still taking on every single value. You might have multiple. Like here, I hit this value a lot of times. But if it's continuous, if you can trace it with your pencil, your function's going to take on every value between f of 1 and f of 4. So this theorem that we're going to lead into kind of like guarantees that, as long as it's continuous. Okay? All right, so here's what the theorem actually says. So I'm going to walk you through another kind of like picture. Choose any interval along the x-axis, a to b. All right. I'm going to do a over here, b over here. There's our interval on our x-axis from a to b. Sketch any function again such that f is continuous on a to b. Okay. I'm going to start here maybe. And again, you don't have to do exactly what I do, but just make it continuous. AKA, connect these 2 points in a curvy fashion without picking up your pencil. I kind of just went like this just to make it like kind of interesting. Yeah, that's continuous. Looks similar kind of to what I did on my paper, but doesn't have to be exactly the same. Okay, locate f of a and f of b on your y-axis. So that's kind of what we were just doing. If a is here, we trace back to find the output. F of a would be here on my y-axis. If b is here, f of b would be here. Okay, I'm just kind of following these steps here. Now, what we just talked about, because f is continuous, it should take on every single value in between f of a and f of b. And it looks like that, right? It looks like I have some values that are above f of b. Here's about halfway, and then it kind of dips below. But at some point, I hit every single output in between that interview. All right, you're going to choose any value y sub 0 that is between f of a and f of b. Okay, so I'm just going to pick this one. Any y value you can pick, call it y sub 0, in between f of a and f of b. Now find the pre-image of y sub 0. That's kind of a fancy way of saying find the x value, so like what value would give us that output, and then locate it on the x-axis. Okay, so where does my function have an output of y sub 0? It looks like over here at this point. So locate it on your x-axis. This would be my pre-image. I'm going to call it x sub 0. Okay, let's maybe do one more. Maybe I'm going to do here. Maybe I picked here. Let's call this maybe y sub 1 this time. So where is this? Oh, there's lots of places. This, I call that x sub 1. Here it also hits my graph, maybe x sub 2. Here it also hits x sub 3. Okay, so what they're trying to get you to see is that you could literally choose any output in between the outputs of your interval, in between your f of a and f of b, and you'd be able to locate some x value that takes on that output, that has that matching output. Okay, now what do we notice about all of these pre-images we found, all these x values? They always lie in between a and b, right? They're always somewhere in this interval, okay? And this kind of like implies off what we know from continuity. So this question is kind of asking, what do the pre-images lie in relation to A and B? They're always in between. Okay, so here's a theorem that guarantees this. It is called the intermediate value theorem. All right, really quick before we jump into this, I just want you to add something into your notes. So I kind of just wrote this above the intermediate value theorem box. So you should have a little bit of room. A quick note about theorems on the AP exam, because as I mentioned, there's 3 of them, and there's always at least one that shows up on an FRQ, on a free response question. Usually, like mean value theorem is really common. I've seen extreme value theorem a lot of times too. So here's our quick note, and I just want to start us early in the correct way of working with theorems in math. Okay, so theorems are always phrased with a hypothesis. So say like if something, so that's kind of like our hypothesis.
Where are we grading this?
Just write it like above your box here. You should have room.
Like right here.
Like right here.
Okay.
Okay. If something, then a conclusion. So what you'll need to do, that's how like theorems are phrased, and obviously we'll take a look at an example in a second. But what you need to do is you must show that all conditions of the hypothesis have been met in order to like apply the conclusion. So you kind of have to like prove or show, hey, this function they gave me does fall under this hypothesis because this, therefore we can conclude whatever the theorem is trying to show you. Okay, and of course I'll always kind of like model the easiest and like most efficient way to kind of like do that for each theorem. But it's good to kind of get this introduced to you guys right away. Okay. So usually with the big three theorems, there's like 2 or 3 things you have to like show first before you can make the conclusion. This theorem in particular, there's 2 things we have to like state in our hypothesis before we can identify or like use the theorem, use the conclusion. Okay, so here is the extreme value theorem. It's pretty much what we just went through, but it's if you have a closed interval from A to B, and our function is continuous, meaning it can be traced without picking up our pencil, it's going to take on every single value in between f of A and f of B, that there's some number in between our interval that would give us that output. Okay, so it's literally what we just kind of like walked through. So we like found some output in between. We like showed, hey, that x value that gives us that y sub 0 is going to be somewhere in between A and B. This is called, oh, did I say extreme value theorem? Sorry, this is an intermediate value theorem. I often abbreviate this as IVT, intermediate value theorem. Sorry, I think I said extreme. This is one of our big 3. The other one of our big 3 theorems. The other one is the extreme value theorem, and then the other one's called our mean value theorem. So this one's important, one of the big 3. I'd say the most common is mean value. This is the second most common, and then that extreme one's usually the least common. Okay, here's what you must state for this theorem. So this is like the hypothesis part. You must state or you must show 2 things. First, that our function's continuous on the interval. Now, this might be as easy as, hey, the function's a polynomial. Polynomials are continuous everywhere, therefore it's continuous on the interval -5 to 7. Okay? Or you might have to go through the steps of showing continuity. It depends on the interval too. But usually it's just they're giving you a function. Is it continuous on this interval? Hey, square root functions are continuous everywhere on their domain. Their domain is, only positives, therefore it's continuous on the interval 7 to 10, if that's what the interval is. Okay? That's the first thing you have to show. The other thing you have to show is that the output that's in between f of A and f of B. Okay, you could also flip-flop this. Usually A is like smaller than B in our interval, but that doesn't necessarily mean f of A could be smaller. Like our function could start up here and end lower. It could be like decreasing on the interval. So it would have to be one of these. you'd have to show that this k value, this is what they're calling k, this k value is in between your two outputs on your interval. So then the intermediate value theorem allows us to conclude, okay, then there's some value, some x value in between a and b that would give us this output, okay? Other things I'd have you write down about intermediate value theorem is it's often used to locate zeros, okay? Basically, this is like kind of easy to detect because they're going to give you like an output that's negative on your interval and an output that's positive on your interval, and like 0 obviously lies between negative 10 and 10, so therefore there's some number that would give us out 0. Yeah.
Does it have to be a maximum minimum point? Because I'm kind of seeing on the graph there's that little like hump at the top. Would that go with the theorem, or would that be kind of a...
No, there doesn't like have to be maxes and mins in the interval. It's just there are two endpoints here. It just happens that that's kind of like the shape of our graph, and that's what kind of a lot of them look like. So no, not necessarily. I mean, we could use this as like it's just a straight line, and we could still apply this theorem. Okay. You don't have to. There goes my star. This next one's kind of wordy. You can kind of put this in your own words if you want. But basically, if there's a sign difference, this is what I was just talking about, in between the outputs, the intermediate value theorem guarantees that there's going to be some 0 in the interval. Okay. So you can write that down if you want. Put it in your own words. The easiest way I can put this into terminology of just like explaining it is because our function's continuous, because we can trace this with our pencil, in our interval here, this theorem allows us to guarantee that all of these numbers in between here take on a value in between our outputs f of a and f of b. That's what this theorem like kind of like allows us to state. I do like that piece because it is most commonly like used to locate zeros. And I think that's actually what one of ours is. Oh, yep. The very first one. This theorem, it actually, like, there's not that much you have to do for the hypothesis. Some of them get a little bit more intense, but this one's not bad. Okay, we'll try two kind of like example problems with these. Here's the first one. Use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1, okay, we got a cubic polynomial function here, has a 0 in the interval from 0 to 1. All right, first thing we have to prove or state is that our function's continuous on 0 to 1, on the closed interval 0 to 1. We know our function is continuous on the interval 0 to 1 because that's a polynomial function. And polynomial functions are continuous everywhere. Okay, that's kind of like the first thing you have to state. Continuous everywhere. Okay. The next thing we have to show before we conclude that there's like a 0, and if it helps you, you can kind of like identify the first numbers are a and b. You have to show that our output is in between our outputs, actually I'm going to order it this way, of f of A and f of B. So what I always start with doing is finding f of A, basically the outputs of my two endpoints. So I'm going to start with 0. So f of 0, I'm going to plug 0 in here to my function, 0 cubed, 0 cubed, plus 2 times 0 minus 1. F of 0 is negative 1. Okay. My other endpoint is 1, so I like to find my output there at f of b. There, we get 1 plus 2 minus 1, we get 2. Okay, so this will kind of help you set it up here. F of A of my one endpoint was negative 1. F of B was 2. So we need to show that a 0, now a 0 on your graph is an x-intercept, right? X-intercept is a 0. So it has an output of 0. 0 is in between that interval, right? 0 is between negative 1 and 2, the outputs of my two endpoints. Now, I'll draw a quick sketch for you guys. What we basically just found, let's say this is, well, I'll use the exact numbers here. 0 to 1. We just found f of 0 is negative 1. F of 1 is 2. So since it's continuous, and since 0, that's what we have to show, 0's in between negative 1 and 2, there has to be some point where we have a 0, where we have an x-intercept. That's what the intermediate value theorem. Okay, so there's our hypothesis. We showed it's continuous. We showed that the value is in between the outputs of my endpoints. So here's where we can apply the conclusion. Therefore, intermediate value theorem guarantees there is at least one. Now, there could be multiple. We know kind of what cubic functions look like, but a lot of these we don't. So how you phrase this is there at least one x equals c value such that f of c would be 0, will give me an output of 0. So the intermediate value theorem guarantees there's at least some c value in between a and b that gives us an output of 0. Now, sometimes it might ask you this. I think this does on your homework. If it does exist, find the value of c. So we're looking for, I mean, you could plug f of c would be like c cubed plus 2 times c minus 1. We want to figure out when that's 0. This is something that we can't factor. C cubed plus 2c minus 1, so we'd have to go to our graphers to solve this. Which I'm so excited to use my new graphing thing. Let's do it. Okay. So you're going to go to your y1. You're going to type in your function, x cubed. Oh my gosh, this is so nice. Plus 2x minus 1. For my window, I'm only looking from 0 to 1. So maybe we could just do negative 1 to 2. And I'm trying to find the 0 where it crosses the y-axis. So I could just change, y to negative 5 to 5. I really kind of want to zoom in on that. You could even go negative 1 to 1 if you wanted to on the y-axis. But we're looking for where it crosses. hypothesis. Okay, so this would be kind of good to reflect on our intermediate value theorem. So again, we showed this on this interval. Oh, bummer. Is it not going to let me draw on this? That's sad. That's okay. We showed our output here and our output here. So there has to be some output of 0 in between those. All right, we can calculate that is second calc. We want to find a 0. Left bound, just get to the left of that x-intercept, hit enter. Right bound, enter. You want me to guess? Yes, I do. That 0 is about 0.4533, ... Okay. Let's practice our 4 decimal places. ... Okay. Does that kind of make sense here?
Oh, you should grab them.
Oh, yeah, sure. Did you get a different number?
I must have put in something wrong.
Does your graph look the same?
Oh, I put -2 instead of +2 for the 2x.
That'll do it. It kind of feels like common sense. You're like, well, yeah, do I really need to state all those things? Because, like, if I have an interval that's continuous, it's obviously I'm going to hit every possible output. Yes, the answer is yes. You do need to state all those things in calculus to apply that. Okay, let's do one more together. Okay, verify the intermediate value theorem applies to the indicated interval and find the value of C guaranteed by the theorem. Okay, here's our function. Here's our interval on 0 to 5. They want us to show that there's some output of 11 and there's some value C in between 0 and 5 that would give us that output of 11. Okay, first thing, we got to state that it's continuous. Why is this one continuous? On the interval 0 to 5. Because it's a polynomial. I told you you'd love polynomials. And polynomials are continuous everywhere. Okay. The next thing we have to show is that 11 would lie between the outputs of my endpoints. So I always just start right away of finding f of a, which is 0 in this case. Okay, f of 0 is -1. And then over here I say, all right, I gotta find the output of my other endpoint, f of b, which is 5 in this case. Let's see, 25 plus 5 is 30 minus 1, we get 29. F of 5 is 29. Now that's not enough. We have to show that 11 is in between -1 and 29. And if it's not, you just say the intermediate value theorem doesn't apply in this case. The IVT does not apply. All right, so we just have to show that 11 is in fact in between. I mean, you could start like this if you want, but I would show it with this notation. This is what you need to show. That 11 is in between the outputs of your 2 endpoints. All right, now your hypothesis is met. You've stated that it's continuous. You stated that that output's in between the endpoints outputs. So therefore, the intermediate value theorem guarantees. And I'm pretty like structured. I just literally use like the same verbiage every time or the same language. guarantees there is at least one x equals c. Oh, I should have the word one. Such that f of c would give us 11, and that's what we were trying to show. Okay. Now this one did say, find the value of c. That's guaranteed by this theorem. Okay. So when I plug in c into my function, I get c squared plus c minus 1. So I need to find that when my output's 11. And this one we can factor. We don't need to use our graphing calculator for this one. Okay. We factor in c plus 4, c minus 3. So we get c values of -4 and 3. Okay. Now, which one of these c values, though, is in between 0 and 5? It's technically on my interval. 3, right? So we don't want to list this one. It's technically not on my interval here. It would just be 3. But you can't have more than one answer. You could get two numbers that are on that interval. Just depends what our function is doing. But this is a parabola. So from 0 to 5, it makes sense that we only have one. And on the other side of our parabola, we have another point that has an output of 11. Parabolas are very symmetrical. But that's our only one on 1 to 5 on the closed interval. Okay. What an exciting day. That's a really important theorem. So keep that note packet in a safe place. We'll revisit these two when we start reviewing for the AP exam.
What was that, like 3-4 days?
When we start reviewing for the AP exam?
No, when we started doing this.
Oh yeah, I know. That was a huge lesson, wasn't it? And I was like, in the end's really important. Okay, we have a few minutes here. I'm going to give you guys the next note packet because it has like a little warm-up problem. So let's let you guys kind of work on those two problems. 1.5 is what we're doing next. So I'll have you guys just try these two problems and then we'll call it a day probably. 1.5, I envision us finishing in one day, Monday. So I'm thinking we'll probably have another quiz over 1.4 and 1.5 over continuity and 1.5, which is infinite limits, on Wednesday again. Okay, 1.5. Go ahead, try these couple problems. Find the value of this limit of this piecewise function, and then practice one of these that we did together. Find the value of a that makes this function continuous everywhere. My hint to you on the first one is because we have this break in the graph at 3, you got to look at the left and the right hand sides. We try to break this up into 2. The limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. And if they are the same thing, then that's what the whole limit is. If they're not the same thing, then the limit would not exist. Both of these we can direct substitute, no problem. Alright, 3 pi over 3 would just be pi. Over here, 9. Cosine of pi. It's -1. 8 minus -1 is 9. Alright. So therefore this whole limit is 9. Because the left and the right are approaching the same thing. That's how you have to split up piecewise functions. Okay, try this last one here. Now, really quickly, why do I know that it's not continuous at 9? Yes.
Because it can't equal 3.
Exactly. We have no piece of this defined for when x is 3. Good job. Even though the limit exists, f of 3 is undefined or doesn't exist. So there's probably a hole. Good job. Okay, this one. Talking about continuity now. We just did a couple like this. Find the value of a that would make this function continuous everywhere. Bell's probably gonna ring soon, so just finish this up. We can go over this as a warm-up on Monday. And I just be making sure that you're working on your kind of 1-4 book work.
Can I ask you a question on the first one?
Oh yeah. Yes, ma'am.
How do you find that on a unit circle? Like,
Pi.
yeah, just
I guess do you like know that 2 pi is the same as like 360 degrees? Okay, so pi is just like half. Like pi is the same as 180. Yeah, you should know that pi is the same as 180. And then if you know that, and you know 2 pi is 360, the rest of it's just fractions. So half of it's pi over 2. Half of that is pi over 4. 3 pi over 4. Well, we'll need to practice some unit circle stuff, it sounds like, huh? Okay, we'll stop there. I'll save this video. You guys have a good weekend.